So in this video on section 4.6 related rates, we'll talk about an idea that I think is kind of new and maybe not familiar with you. So it can be a little bit challenging too. So consider the area of a circle. Area A equals pi r squared. So in this scenario, the area depends on the radius. So we would say the change in the area would be represented by dA dr, the derivative of area with respect to the radius would be just 2 pi r. So r is the independent variable and a is the dependent variable. Straightforward calculus example. Now consider a problem where the radius changes with time. So for example, imagine you drop a pebble into a calm pool of water, and if you follow the path of one ripple of water, that defines a circle, and then as that ripple expands, it shows that that radius of that circle is changing with time, and then as the radius changes, so too does the area change with time. So now what's really happening is our area equals pi r squared has really become an a of t is equal to pi times r of t squared. So then when we go to take the rate of change of the area, what we're really doing is we're going to take the derivative with respect to t. So t is the independent variable. And what we get then is dA dt is going to be, and now the derivative of pi r of t squared becomes a chain rule derivative. We're going to get pi times r of t to the first, and then times the derivative of the inside function r, which we typically call, in this case, dr dt rather than r prime, because we usually want to kind of emphasize the fact that it's the t that's the independent variable here. So that would make more sense, but unfortunately, it's not usually written in that kind of notation. That is, we will not be writing those of t's, the area of t and the r of t, but from the context of the problem, we'll have to understand that the t is actually the independent variable, and then we'll have to then figure out that what we're getting is this dA dt is 2 pi r times dr dt. And so it's the context of the problem that's going to help you figure out and give you clues to the fact that we're actually differentiating with respect to t. So here is one example in the green. Suppose we have a cylinder and its radius is 5 inches, but the height is changing with time. So in this case, the radius is fixed. It's always 5, but the height is changing with time. So that means that our volume of a cylinder formula, V equals pi r squared h, since the radius is not a variable, we can just plug in the 5 for the radius and make that 25 pi times h. Then we can differentiate this formula with respect. I bumped it with my hand again and made it save. So dV dt is going to be then, it's going to be 20, lost my pen, hard to write this where it is, 25 pi times dH dt. And that's going to be our derivative of that volume. Now let's make it a little more complicated. Now let's consider a case where we have this time a cone. So we've got this cone, and the volume of a cone is 1/3 pi r squared h. And this time we're imagining that both the height and the radius are changing with time. So now when we go to differentiate this with respect to time, we have to be careful, because if r and h are both functions of time, when we go to differentiate it, we have to use our product rule. So I'm going to call the 1/3 pi over 3, and then we're going to get a product rule, the first r squared times the derivative of h, the second, which we'll call dh dt, plus the second h times the derivative of the first, which, because r is a function of time, is going to be a chain rule derivative. 2 times r to the first times the derivative of r, that inside function, which we'll call dr dt. So it's going to be really important for you as you read problems here and to try to get from context which things are variables and which are not, because that makes the derivative much more complicated. Okay, that's all I'm going to do on this, but then we're going to have a worksheet with some examples. So I'm going to switch over to that.